probably don't have to be a physicist to know what static electricity is. I'm sure that you've all had clothing stick to clothing, you've had sparks when you took sweaters off, and you've probably gotten a balloon to stick to the wall by rubbing it on your head. Static electricity is produced when two dissimilar materials rub next to one another. And almost always, one material has more of an affinity for electrons than another. In other words, one takes electrons and one gives electrons. This cannot be figured out theoretically very easily, and so mostly it's done by experiment. The equipment we're going to use for this demonstration is pretty simple stuff, a couple of balloons. So instead of a single string, we've got a V of strings, which limits the ability of the balloon to move in the plane of the V and lets it move very easily at right angles to that. So we're going to start by charging the balloons. We're going to rub the balloons with fur. We're going to notice the balloons no longer hang vertically. Apparently, there is a sideways force between the balloons in addition to the vertical force from gravity. We are then going to take that same fur and rub the PVC rod and take a look at how the balloons react. The acrylic rod, when rubbed with cotton, is going to attract the balloons. And this was an important experiment done by the early scientists studying electricity, because it showed them that there was a second kind of charge. And so we've now got two charges, the charge produced on this acrylic rod and the charge produced on the PVC rod and the balloons. And we have discovered that like charges repel and that unlike charges attract. Remember, we said there are two different affinities for electricity, and one of these two different materials gives up electricity and the other one takes it. And so the fur is going to act differently than the rod. And so if we bring the fur near the balloon, we discover that, unlike the rod, the fur attracts the balloon. This was work done first by Ben Franklin, and it indicates that we are not creating charge, we are redistributing charge. And Franklin's realization, which really is what makes Franklin a famous scientist, was that electric charge is conserved. If we produce charge in one area, we do that by moving it away from another area. So a Van de Graaff generator looks really high-tech, but it turns out we're making static electricity just like we did when we rubbed the balloon. The difference is that we're doing it automatically by using an electric motor to turn the pulley, and the belt with the charge on it goes up to a metal ball suspended on a plastic insulating tube. The charge builds up on the metal ball until we have a lot of static electricity. The spark jumps because there's somewhere that has less negative charge for it to go. Don't try this with your house wiring. I'm not getting hurt because despite the high voltage, this generator makes only a tiny current. Next, we're going to put a stack of pie plates on top of the Van de Graaff generator and see what happens. It turns out that the pie plates are pretty light. They're aluminum foil. If we get enough charge on the top pie plate, the repulsion of negative charge from the other negative charge on the ball exceeds the weight of the pie plate. And that pie plate lifts off and moves away, taking that charge with it. The belt's still running, the charge is still being delivered, and the new charge now moves to the next most distant pie plate, now the top pie plate. The same thing happens. When we get enough charge on the pie plate, it lifts off and moves away. So the pie plates actually show us the delivery of charge from the belt to the top of the Van de Graaff, and they move off one at a time as a bucket brigade, removing charge from the ball every time the repulsion gets to be greater than the weight of the pie plate. The next demonstration we're going to do is a little different because I'm going to be part of the apparatus. If I stand on the floor at the voltages produced by a Van de Graaff generator, I'm not insulated. So I'm going to stand on a plastic box. I'm going to ground the ball of the Van de Graaff with the wand, and what that does is it takes away the electricity while I put my hand on. In other words, it keeps me from getting a stinging spark as I'm doing this. So I put my hand on there and then I remove the wand, and now the charge is going to begin loading onto my body. It takes a little time. My body is a lot bigger than the ball at the top of the Van de Graaff. And as my body builds up charge, just like those pie plates that we saw before, my hair is rising and beginning to radiate from my head. The direction that my hair is going is the same as the direction of the electric field. So in a little way, I've become a 3D diagram of the electric field. The way I finally escape from this is I take my hands off the ball so the charge stops building up on my body, but it doesn't go anywhere because I'm still insulated. Now I step down off of the box. When my foot touches the ground, there is an escape route for the electric charge. Gravity takes over, and I'm back to my good-looking normal self.